I'm Ethan Kwan, and today I'm going to be telling you about atoms, the real deal. Okay, so here's what you're going to learn here. So how to determine what atom is where on the periodic table, how to plot an electron configuration and write it down, why the electrons are the actual funnest part, what loose dot structures are, what happy atoms are, and why these pieces of info are getting smaller. You heard me. Anyway, so to start off, we need to know what a periodic table is. A periodic table is a group of elements that make up the universe. A better way to describe the periodic table is a group of elements that tell you what each thing is, but it's not really if you zoom in and you see atoms for each example. Here's a sort of accurate model scale. So here's the nucleus, and I'm just going to make the electron go one time around the nucleus, and then I will show you where it is. Going round and around and around. Almost there, almost there, almost there, almost there, almost there. And there. Right there. Right there. Okay, so I'm just going to draw the electron in the top corner. Top center, I guess. Right there. Okay, and so here's a model for scale. So if the atom were the size of a soccer field, a soccer stadium, and the nucleus was a soccer ball, then the nucleus was a soccer ball, then the electron would be a fly buzzing around the spectator, just like this. And there it goes. Ooh, it just went into a net. Good. Ooh, it bounced off and went into the other net. Cool. I'm just kidding. Anyway, so here's the periodic table. And before I do anything else, I'm just going to say it's really beautiful. How big of a geek am I to say that? Anyway, so in the universe, 75% of it is hydrogen. But if you count dark matter and dark energy, it's only 3%. And everything else, 1%. So now you're probably asking, well, what are we made of? Turns out there's actually a shirt for that. Awesome, right? Now you're probably asking, what is that barcode doing down there? Strange. Anyway, so from here, let me just get rid of all the elements that are not in the human body. Ta-da! So clear. And now you can understand funny t-shirts like this. Genius! Cool. Now, what do atoms look like? Like this, right? Very easy to understand. Wrong. The atoms are pretty hard to understand. Here, here's the most accurate model I have. Imagine cotton candy, and I give you this piece of cotton candy. Now, before you get to eat it, I ask you, where is the sugar? And if you can't answer this, you can't eat it. Well, then you probably can't eat it. Because it could be here, or here, or here, or anywhere, like here maybe. Anyway, so that is an electron going around the nucleus inside cotton candy. We can't really know where it is for certain. We can only predict. Okay, but I'm just going to use this normal fun model that's easier to draw than the snack model, the candy model, whatever it's called. I forgot what cotton candy, right? Anyway. Now I'm just going to focus on this top part. There we go. Okay, so I want you to focus on two numbers, atomic number and atomic weight. So the atomic number is the number of protons, and the atomic weight is the number of protons plus the number of neutrons. So for example, carbon, atomic number is 6, because that's how many protons carbon has. And the atomic weight is the number of protons plus the number of neutrons. So this time it's 12.0026. So the atomic number is 6, And you can't really change this number, because if you increase it, it's nitrogen, and if you decrease it, it's boron. So now I want to focus on these three isotopes, 12, 13, and 14. That means there are 6, 7, or 8 neutrons in the nucleus. I never said the neutrons can't change. Where's that cat doing there? Anyway, so 14, you're probably familiar with radiocarbon dating, and we use something called a half-life. Now, I'm going to give an example with an atom that has only 1 minute of a half-life. So that means that after 1 minute, it's going to be half of what you started with. So let's say you had 100 atoms. Now, after 1 minute, you're going to only have 50 of them. And then after 2 minutes, you're going to have 25 of them because it's half of half. And then you're going to have like half of 25 of them after 3 minutes, and so on. It's an exponential decay. But carbon 14's half-life is more like 5,000 years. So every 5,000 years, it decreases by half. It's not like it stays 100 and then it decreases by 50 once it becomes 5,000 years. It's just like a slow decay. But let's get to the most important part. You have 3 guesses to guess what the most important part is. It is the electron. So I'm going to talk about happy atoms. So an atom is happy if, and only if, that atom has its outer shell of electrons is full. And that defines a happy atom. So the only happy atoms by themselves are the noble gases. These ones. The ones that I boxed. So, for example, here's a model of helium. And of course, this is entirely incorrect, but just go with me. And it just goes around and 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 so on 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 and so on. Got it? Almost there. It's stopping. Yes. Why is it still like crackly? Anyway, so if I put a circle above the smiling face, that means it's a happy atom. And if I put a circle above the frowning face, it means that it's an unhappy atom. Now, I'm going to give you a model of hydrogen with 1 electron. Now, this one isn't happy because it doesn't have a shell full. Now, helium, on the other hand, is. Now, if you add 4 atoms, then it's going to be some other atom. I think carbon or something. Carbon isn't happy because, well, its shell isn't full. Now, if you put neon, it's happy because it has a shell full. Now, if you add 4 more, then it isn't happy. And if you add 4 more than that, it is. Kind of got it? Okay. So it seems like the most important outermost shell is the most important thing. So why don't we focus on that and ignore everything else like this? And if you're thinking that, you're not alone. Gilbert Lewis. And that's how he came up with the Lewis structure of dots. Wrong. Oh, it's falling apart. The Lewis dot structure. So a Lewis dot structure is just like a model of the outside. So you ignore everything and count how many how many electrons are on the outside. And the ones on the outside, you just put that many dots around your symbol. So, but don't put E's. You're gonna fail if you have a test like this. Get rid of the E's and put dots instead. Actually, too big. Yep, that's better. Just a little bit closer, maybe? Okay, anyway. So,